All right, guys. We're going to get started on understanding how tangents work with circles. So let's get going on this. All right. So tangent lines and circles. So the first thing you remember that a tangent line is a line that intersects a circle only once at exactly one point. Okay. Now this is the big thing. This stuff down here in red. Also, the tangent line is perpendicular to the radius at the point of tangency. So wherever it intersects that circle, that exact point, when you draw the radius from the center to that point, it's going to create a 90-degree angle. Okay. So this one, I'm asking you, is the segment tangent to the circle? Well, if it is going to be tangent, that means that angle A right here is going to end up being 90 degrees. Now, the way that we can prove that is by using the Pythagorean theorem, a squared plus b squared equals c squared. And I would just put in my legs, 9.6 squared plus the 7.2 squared should equal the 12 squared. Now I've got the 92.616, that's the 9.6 squared. And then 51.84 is 7.2 squared. And then 12 squared is 144. So when I add those two parts together, I do get 144. So what this tells me is because this is true, that 144 equals 144, that this has to be a right triangle. And so that's telling me that if this is going to be a right triangle, that this angle A right here has to be 90 degrees. So the triangle must be a right triangle. So segment AB must be tangent to the circle. All right, now for this one, we're going to do the same thing. Okay, we're trying to see if segment BA is tangent to the circle. So we're going to use the Pythagorean theorem again. But in this case, when we go through and we simplify, and we take a look at this, we've got our 6.3, that's one leg squared. Now on this one, we had the radius be 4.2. So if the radius is 4.2, that means that that whole diameter is going to be 8.4. And 8.4 squared is a 70.56. So we add those two together, and they do not equal 9.4 squared. So because they are not equal, this means that they cannot be a right triangle, and that means that that segment cannot be tangent to the circle. All right, now on this one, we're going to find the length of the segment. Now this segment right here is just the part that's on the outside of the circle. Okay, so the first thing that we need to notice on this is that we have two radii of the same circle. So if this radius is 4, that means that the other radius is going to be 4. All right, now we can use the Pythagorean theorem, and I can say that the 4.2, because that's one leg, squared, plus the radius, that other leg squared, is going to equal whatever that is, this question mark, plus this radius 4. Okay, now on this part of it, I've changed the question mark to x just so that it's easier to work with algebraically. So once we simplify this out, now I've got 17.64 plus 16 equals x plus 4 squared, the quantity of x plus 4 squared. Now, when you multiply this out, you can use an area model or the distributive property twice, but you're going to end up with x squared plus 8x plus 16. Okay. So now this one is looking like, oh, well, how do I solve for x? Okay. Well, this is quadratic. Okay. We just have to make it equal to 0. So over on this side, I've taken this 33.64 and I've subtracted it to this other side. So now we have a quadratic equation that's equal to 0. And we just need to solve the quadratic equation. So we can solve it by completing the square. If this was factorable, this is not factorable though. On this one, I chose to use the quadratic formula. And I'm not going to show all of the quadratic formula, just the last little bit of it. Okay, so if I substitute that in and we use the quadratic formula, then I'm going to get two solutions, 1.8 and negative 9.8. Okay. Now, when we take a look at those two solutions, they are both solutions to this quadratic equation, but only one of these solutions actually makes sense with our situation. And that's the positive one. So it has to be 1.8. So if that little segment that's on the outside of the circle is 1.8, that makes that whole hypotenuse 5.8 units because we just have to add that radius back into it. Okay, so reviewing this, we use the quadratic formula. we put in x for this unknown piece, and that those two are radii of the same circle. So if this radius is 4, that piece of the hypotenuse is also 4. And then we solve the quadratic equation by using a quadratic formula and taking the positive solution as our solution, because this is a distance and we can't have a negative distance. All right, so now on this one, we're told that segment BC is tangent to the circle. Okay, we have a central angle here that's 102 degrees. Okay, and we're asked to find the measure of angle C. So when we take a look at this, we have 3 radii in here. Okay, now the 2 I'm going to focus on are OD and OA, because we have this little triangle that's ODA. Now those are both radii of the same circle, so that's going to make this ODA triangle isosceles. Okay, so we have those 2 pieces are congruent. Now we know about isosceles triangles that if the sides are congruent, then the angles that are opposite those, or the base angles, are also going to be congruent. So I can say, all right, these 2 are going to be congruent, so they all have to add up to be 180 degrees. So if I just subtract 180 degrees and the 102, then I can just split the remaining degrees between those 2 angles. So they have to be 39 degrees. So each of those angles inside of that triangle have to both be 39 degrees. All right, so now I'm going to draw your attention. We have a larger triangle. We have triangle ABC. Okay? And if we know that BC is tangent, that means the radius to the point of tangency is going to be perpendicular. That means this angle's got to be 90 degrees. Okay, because we know that that is tangent to the circle. Now we have 2 of the 3 angles in that large triangle. So I've got this 39 degrees, the 90 degrees there at the point of tangency, and now I just have to figure out angle C. So I just have to subtract that from 180, so angle C has to be 51 degrees. All right, now another part about tangents is because you can have more than one tangent to a circle. Okay, so these are, all 3 of these red lines are tangent to this circle. And if you have 2 tangent lines drawn from a single point that's outside the circle, then the distance to those points of tangency have to be congruent. They're the same. And I've marked that congruency on this diagram. So now with this situation, I've given you parts of the pieces of the side lengths of those distances from the points to the point of tangency. And I want you to find the perimeter. Okay? So if we look at RB, we know that's 6. So that means that the segment BS has to also be equal to 6. Okay? So I know that this piece has to be 6. Then I can do the same thing over on this other side. And if AR is 4, then AT has to be equal to 4. Now I've got this whole side, AC is 12. But if I know that AT is 4 and the whole thing is 12, then I can say that TC has to be equal to 8. And if TC is equal to 8, then CS also has to be equal to 8. And now I can just add up all my pieces. So I've got the 4 and the 4, the 6 and the 6, and the 8 and the 8, all the pieces of that perimeter. And then my perimeter is going to be 36 units. All right, we're going to move on from here from tangents to the way that secants and tangents and chords all interact with each other. And I'm hoping that as we do these videos that you're getting used to how all of these different parts of the circles interact. And remember that you can always ask for help and help each other.